Here we have an absolute value function that follows all of the rules that we discussed in our earlier lesson on absolute value functions. You'll see the minus 5 on the inside of the absolute value. That shifts the vertex 5 units to the right. You'll notice the minus 3, which shifts the vertex down 3 units. And you'll notice the 3 on the outside, which serves the purpose of making the two sides of the absolute value function steeper. If for some reason we did not have this function already given to us, and we had to create our own function to model this situation, we might have an easier time, instead of trying to determine that absolute value, to instead just dive right into creating the piecewise that would map the same situation. So we're going to temporarily put away the absolute value and look only at these two line segments. We see that we have a point down here at the vertex. That will be helpful when it comes to graphing. And if you noticed, we had defined the two ends as well. So we have a point here and a point here. We know that our domain, and we can get this from just inspecting the graph, extends from 2 to 7, and we can see that our range extends from -3 to +6. Creating the equation for the piecewise version of this function is just a matter of looking at the two pieces separately. So, looking at the first piece, we can see that the first piece extends from 2 to 5. So we'll set our domain so that the first piece extends from 2 to 5. The second piece is going to extend from 5 to 7. Now, because we have overlap at the vertex, we want to maintain the fact that this is a function. I don't want to just throw out that it goes from 5 to 7 inclusive, because the 5 may or may not be there. But since I included the 5 up here, I'm not going to include the 5 down here, and I'm going to say that this goes from 5. The second part's going to go from 5 to 7. If I look at the two different parts of this graph, I can easily calculate the slopes of each one. From this point at the vertex to the top right point of the positive side of the function, I'm going to go up 6 and over 2. That tells me that this side has a slope of 3. You can notice from symmetry that we follow a similar pattern over here. I don't have to extend all the way to the top of the graph. I can see it just by going from that same height and across, that this section is going to have a height of -3. And I'm going to use both of those numbers to help me determine the equations of the lines. For the section on the right, since that has the positive slope, it's going to use the vertex that we can find at the point 5, -3. Y plus 3 equals 3 times x minus 5. There's our point slope form. We're going to distribute out the right-hand side, and we're going to subtract the 3, and we're going to end up with y equals 3x minus 18. If we do the same thing to the other side, we can write an equation for the other side for our model. So again, y plus 3, this time our slope is -3, and x minus 5. Same thing, we're going to multiply out the right, -3x plus 15 minus 3, y equals -3x plus 12. So our two parts of the graph will be -3x plus 12, which matches the slope we found from looking at the picture, and the equation 3x minus 18. If you want to convince yourself, you're welcome to graph on top of these two, but it does seem like this line would go all the way down through -18, and it certainly does seem like this line would keep coming up here and go through 12. So a quick look at our two y-intercepts. They seem to make sense for the setup that we have, but here is our piecewise function version of that absolute value graph.